I'll head it.
Okay, thank you. Welcome everyone to the second lecture in this week's series of lectures by Andrea Montanari on mean field methods for high dimensional statistics and non-convex optimization. It's a series of lectures that was initially designed as part of the Séminaire de Mathématiques Supérieures, but we're happy that we've managed to, despite circumstances, maintain it for online for this week. Today's lecture will be approximately 1 hour. It will be recorded, so in case you do not wish to be recorded, please turn your video off and your audio off. You are welcome to, all the participants will be muted, but you're welcome to ask any questions over the chat. And we will notify Andrea, either someone will answer your question in the chat or we'll ask Andrea for a clarification. There might be a short break in the middle of the lecture. Once the lecture is concluded, we will have approximately a half-hour break followed by an exercise session starting at 1:30 p.m. Eastern Time or 17:30 UTC or 10:30 Eastern, Pacific Time. And the exercise session will be led by Michael Santano. The exercises have been posted on the OOPS website, so you're welcome to download the file and take a look at it. And in between the lecture and the exercise session, we will open up some breakout rooms in case you wish to discuss some of today's lecture a bit longer than after the questions period after the lecture. Okay, so I'll leave it to Andrea now. Can you spotlight his screen, please, Thomas?
Yes.
Okay, I'll share. Thank you, Leah. Share my screen. Okay, so here I'm starting. Thanks for coming again. Okay, so I'll start this lecture by a brief summary of what we did in the last lecture. So I described, very briefly what is one main motivation for this line of work is statistical inference or statistical estimation better. So this is, the standard setting is that you have a probability distribution parameterized by a vector theta, p theta, and you sample, n data points from this probability distribution, and your goal is to estimate the parameter theta that these n parameters come from, n samples come from. Okay, so you use for that objective an estimator theta hat of z that depends on the n parameters. So this is the vector of all the samples. And a standard way to construct such an estimator is to minimize a cost function. And most often this cost function we said as this following structure is the empirical average over the sample of a loss. Okay, so this is this first term. And then, perhaps there is an added regularization term. And we studied a little bit in detail this example that is sparse regression, also known as the lasso. This is, a simplified somehow version of this example. This is a problem in which you have parameters, your samples, they take the form of yi, xi, where xi are it's called a feature vector. So let's say that is, in a simple model is Gaussian with identity covariance, and yi is a linear function of that vector plus noise. Okay, just to make it, to make an example, this is, the typical model that you use for predicting, all sorts of things using statistical modeling. For instance, predicting click-through rate in a internet service. Of course, this is much simplified with respect to what is done in practice, but at the core, that is the kind of problems that we have in mind. And the typical loss function, the typical risk function for this, a typical risk function is the lasso, in which you minimize y minus x theta. So x is the matrix that is n by d, and as rows the xi's. So this is the matrix which has as rows. So this is the matrix x1, xn. So this is n by d. And then you know, so this is minimizing exactly the sum over I, yi minus xi transpose theta square. Okay, so this is exactly this objective. Okay, so it's minimizing the residual sum of square, and okay, you add for regularization a penalty of this form to promote sparsity. And we studied what is, you know, how to use Gaussian comparison inequalities for compute the limit value of this quantity. Okay, what I want to talk about today is, okay, how do you actually do this minimization problem? So you want to minimize, for instance, this cost function. How do you do it? And okay, you know, of course, there is, you know, a vast literature on this on optimization, but the simplest point to start from is gradient descent. Okay, so gradient descent. Okay, so this is probably something that everybody heard about. Okay, but this, you know, is basically doing, it's an iterative algorithm in which you go in the direction of the gradient of descent. Okay, and this here, this ST are step sizes. Okay, so you can think of this as fixed or as a, you know, pre-decided sequence of real numbers. Okay, now there is a subtlety here, of course, is that, for instance, in the specific example that I gave you before, this lasso, the function is not differentiable, so the gradient in general doesn't exist. But okay, you can you know, solve that problem using a variety of methods. One is using, you know, subgradients instead of gradient. One other is using something that is called proximal gradient method. And there is a variety of improvement, of course. This you know, gradient is attributed to Cauchy normally, and since Cauchy there has been some progress. So for instance, there is a class of algorithms that are provably faster at the same computation speed, and these are called the accelerated gradients. And other type of very interesting algorithm are what is called mirror descent, and so on. Okay, so this is a huge literature. One thing that all of these algorithms, of course, I don't want to go into this, but one thing that is all these algorithms have in common is that these are first order methods. So this is optimization terminology, and it refers to the fact that they access the loss function only through its gradient. Okay, so as you see, what you do at each iteration, you compute the gradient of the function and you do something with the gradient. This is the general definition of first order method. Okay, it has to be a little bit formalized, but okay. So so can we do a general theory of these first order methods? You know, in optimization, there is such a theory that concerns mainly convex functions, but here we want to, you know, kind of look at a theory that exploits the statistical nature of the data. So what is the common structure of these first order methods? Well, you know, we have a little bit to specialize the problem, so I'll specialize it to the kind of problems that I described before. That is a regression problem, in which again the response is data as the form yi xi, where yi perhaps is a response and xi is a feature vector. Again, think for instance of xi, kind of all the information that concerns the patient, and yi the outcome of a certain procedure on that patient. And then you want to minimize a loss function, and in general this again I write it as a function of zi and theta, but I will specialize it by writing as a function of yi and theta dot xi. Okay, so what I'm trying now to minimize is ln, let me write it ln of theta, that is 1 over n, sum over I of L of yi theta xi. And if I write this in vector notation, I can write this as 1 over n L of y and x theta. And here I use this convention that I'll follow from here on. That is, when I have a function, scalar function applied to vector, is understood that is applied, or to a couple of vectors, is understood that is applied entry-wise. Okay. In this case, it's applied entry-wise and averaged. Okay. Now I need to compute the gradient to do gradient descent. So what is the structure of the gradient of this? This is, if you do, it's just x transpose times a function of y and x theta. Okay, where this function is what? Well, this function is very simple. It's just the function of first derivatives, right? Okay, so perhaps I should. Okay. And here f of y is the partial derivative with respect to y hat of L of y hat. Okay, so with this, now we computed the gradient. So the structure of gradient descent is simply that theta t plus 1 these are some deterministic number st, and then there is xt. Okay, so what we see here is that we are doing two types of operations, right? One type of operation is that is multiplications. Or X transpose by matrix vector multiplication, and the other is we are applying a separable function. So we are doing two types of operation here. If you look at it, we are multiplying by X transpose, and then we are applying this function f. Okay, so what I want now to do is, this is common to all the list of algorithms that I described before. They all proceed in this way, or many of them proceed in this way. What changes is the order in which you do these operations, and then the type of functions that you apply. What I want to do is just abstract this and look at general class of algorithms that are constrained to this kind of operations. Okay, so because of that, I'll define something, okay, that I'll call generalize first order methods. And this takes the following form. So at each operation, you do X transpose times some function of the previous iterates. And then perhaps of Y. Perhaps I'll erase this. Plus some other function of the previous iterates. And perhaps here I have some side information. And then I update another set of vectors in the same way. Okay, so this is what we call generalized first order method. So I have two sequences of vectors, the UTs and the theta t's. The theta t's are supposed to be estimates of my parameter vector, and the UT are auxiliary variables. And each so one, the UTs are here. So there are two different dimensions, right? The UTs have dimension n, and the theta t's have dimension t. And at each operation, you do one of these two things. You either, compute a function of all the previous iterates, or compute a function, or multiply by x, or multiply by x transpose. Okay, and here the f are supposed to be, functions. For instance, ft will be a function from r t plus 1 to r. And when I apply two vectors, as I apply it here, this is f1. It's understood that it's applied entry-wise. So I form, I look at all the vectors of first coordinate and I apply the function, the vector of first coordinate, apply the function, and so on. Okay. So does this definition make sense? So this pretty much any first order method, for this type of problem fits into this framework. And in particular, gradient descent, accelerated gradient descent are easily seen to be special examples of this algorithm. And it's very difficult to come up with things that don't fit this type of algorithm. Now, this does include other type of algorithms that are called second order methods, for instance, Newton method. This is the limitation of the framework, and in a sense, Newton method is a powerful method, but in high dimensional statistics is not that much popular because it requires inverting a big matrix, and you don't want in practice to be inverting big matrices, right? Okay, now the question is, can we analyze general and possibly find the best one? And here, when optimal one, we mean statistically optimal. Okay, there is a large theory that tries to find the best first order method from an optimization point of view, but this is not clear that it implies really the best algorithm from a statistical point of view. okay, that is on random instances. Okay, and okay, so we can do this in a few settings, in a couple of settings. So here I fix a specific setting for this lecture. So the answer is positive, and in some conditions. So I'll fix one specific setting in this lecture, and then in the future lectures I look at another setting. The setting that I look at in this lecture is again regression, and it's a generalization of the lasso problem that I described. So I'll have my matrix X. So this is my matrix whose rows contains the covariate. I'll take them to be IID normal 0, 1 over n. And here the fact that they are normal is not very important, but it's important the fact that they are IID and okay, centered. And okay, the variance is scaled in the right way, to make things convenient. And I'll take n over d to go to delta, okay? So this is some number in 0 infinity. So these are rectangular matrices, but with aspect ratio that is of order 1. And then I'll assume that I have responses yi that are some function h of xi transpose theta naught and some noise. So think, for instance, as the noise as normal 0, 1, doesn't matter really. And h, for instance, sufficiently regular. Okay, so this generalized the special case of lasso where this function h is the sum, and then I'll take this theta 0, so the true vector, and then you have this theta tilde that appears in the iteration is really meant to be an initialization. So the theory includes the possibility of initializing with something correlated with the truth, and I'll take this as IID with some probability distribution mu of theta 0, theta tilde, and this is a probability distribution on R2, and the WI, okay, the WI we wrote it normal 0, 1, doesn't really matter. Okay, in general I can call this distribution mu W. Okay, so I can.
Andrea?
Yeah.
Okay, so we had a question about why we include earlier more than just the previous iterate, and I responded that methods like accelerated gradient descent require more than just the previous iterate in their update. And then we had a follow-up, which is, what is the intuition behind including previous thetas? Do you have a good answer for that?
A good answer for that. A simple intuition. Well, okay, so there is something that is simple. There is a simple intuition beyond. There is one method that includes a memory term. So for instance, this accelerated method that Michael mentioned is including t plus 1, t and t minus 1. Okay, and if you include it in the right way, this achieves the optimal convergence rate for optimization in certain setting. For instance, smooth strictly convex functions. So why you need the term t minus 1? I mean, there is one intuition, but it's not completely correct, that there is this class of methods that were studied in the Soviet literature that are called heavy ball methods. And so if you think of gradient descent is really a discretization of something like this, right? Now, turns out that when you discretize it, this overshoots. So the classical situation in which it overshoots is this one, right? You have a quadratic function that is very, anisotropic, and gradient descent, if the step size is not exactly right, we start doing these kind of things, right? So we'll converge, but we'll converge slowly because, you know, at this point here, the gradient is in this direction where the minimizer is down here, right? And so okay, so because of that, you might want to add a memory term, a second order term. So you can try to do instead the following: you discretize this. Okay. And in fact, accelerated gradient is basically a discretization of this. It's a second order thing, and this reduces this kind of problems. And okay, one way to think of it is that you have, you know, again, as the word says, a heavy ball. So, you know, a system that has some friction, and you carefully tune the friction as to converge, you know, as quickly as possible. So, you know, if you want to discretize this, now you need at least 3 times. I mean, that's my answer.
Okay.
I don't know if, okay. Okay, so let me go ahead and, okay, so this is the setting in which I'll study this moment, these methods for this lecture, and let me now state a theorem. I state it without all the details, but just to see where we are going. So we can prove things of this type, okay, for this model, for any GFUM. So for any method of this type, we have a lower bound okay, so this is, you look at the lower bound, you look at the estimation error after t iteration, fix t, and let n and d to infinity to have a fixed ratio, and you have an explicit lower bound, okay, where so at t is explicitly given. And I will not describe it here because it's explicit, but is defined recursively, and I don't want to down the recursion, except in special cases. But the interesting fact is that further there exist special GFUM that I call base NP. That achieves the lower bound in the sense that the lim this is equal, okay, and okay, so in the rest of the time today, I don't know, okay, today and tomorrow probably, I want to provide some meat to this theorem, and okay, so let me describe at high level what is the proof scheme, and not just for the sake of learning this theorem, but because, you know, this allows me to explain, you know, a bunch of other concepts. The high-level proof idea is, first step will be a reduction from the general class of GFUMs to a subclass of algorithms that I'll call the approximate message passing algorithms. And I will describe just the content of the reduction, but not the reduction in detail. It's not particularly instructive. And then I'll describe the fact that this AMP algorithm can be analyzed in a sharp way in this limit. And finally, argue that this special algorithm, Bayes AMP, is optimal. Among AMP algorithms for this problem. Okay, so this is the scheme of the proof and the plan for this lecture and at least part of the next. And I want to I will not describe all this step in detail because it's a bit technical and not very useful. But I want to start by describing an example in which I can write things a little bit more easily. And this example is again the sparse linear regression. Okay, so now this example is instructive, and because things can be understood very easily, is a little bit is not the example that is most interesting because it's a convex optimization example. So there is a lot of theory for optimization in convex optimization that has already important implications here, but okay, the interesting fact about the theory that I'm trying to describe is that applies also to non-convex example. Here I didn't assume in any point convexity. Okay, so let me perhaps describe a non-convex example just at the level of example, just at the level of defining it. Okay, so first example perhaps. I want to give you an example of a non-convex regression problem. And this is what's called phase retrieval. It's a very nice problem in which you have an unknown vector theta naught. And in linear regression, what you do is that you measure, you can think of linear regression as you measure linear projections of this vector theta in random directions. Okay, so you measure the scalar product of theta naught times xi, where xi is a random vector. All right, so this is linear regression. And perhaps your measurements are noisy. So you measure the projection on this, and geometrically, therefore, what you're doing, geometrically, what you're doing is that you have this vector theta naught, and then your vector x1, and perhaps x2, and you project this here, and you project this here, and you measure these two quantities. Okay, so it's the problem geometrically is basically intersecting a set of hyperplanes. Now in phase retrieval, what you're doing is this. So you measure the square of the scalar product. So you are trying to solve a set of quadratic equation. And one way to solve it is to minimize the cost function. Okay, so this is the same least square objectives, but now there is the square inside. Okay. And okay, so now this is immediately a non-convex problem, and so all sorts of crazy things happen. Okay, so this is an interesting example. I don't want to go into this. I want to use a simpler example to describe the general theory. So I'll go back to the linear regression problem, and therefore sparse linear regression, and therefore my cost function now for this example will be this one. Okay, so I close the parentheses of phase retrieval. And okay, let me describe what is proximal gradient here. Proximal gradient proceeds in this way. Okay, so this is a specific algorithm is proximal gradient descent. Here the function eta, we should define what it is this function. Is constant between minus alpha and equal to 0 between minus alpha and alpha, and is equal to, is linear, it's affine outside. This is this function. It's called the soft thresholding function. Okay, so this algorithm, if L is an upper bound on the maximum eigenvalue of XX transpose, then this algorithm is guaranteed to converge to a global minimum of this cost. Okay, and okay, there are various ways. It's basically gradient descent in which you take into account, by this function, you take into account for the fact that this regularizer is not differentiable. Yeah? So this is a very, it's probably the simplest and one of the most popular algorithms for this problem. I want to instead describe another algorithm that is an AMP algorithm for this problem. Perhaps I should say a word about how is this derived. This corresponds, one way to think about it is that you take your cost function and you compute an upper bound that is a quadratic upper bound of this portion, and then you minimize at each step that quadratic upper bound. Now instead I want to define another algorithm that is this approximate message passing algorithm, and this takes instead this form. Okay, so here there is very little changes between these two algorithms. Notice one thing that changes is that I allow me the liberty of choosing a different threshold at each level, at each step. I remove this 1 over L constant here, but the most crucial part is that I added this memory term here. Okay, again, it's not hard to check that the fixed points of any of these algorithms are actually minimizers of the cost function. Okay, now the nice thing about this AMP algorithm, so this is both are first order algorithms, but the nice thing about the AMP algorithm is that one can prove a precise characterization of its asymptotic behavior. And this takes the following form that, if you look at the empirical distribution, and so I look at what? I look at the pair of vector theta naught, which is the true vector, and theta hat t, theta t, which is my estimate. Okay, so these are two vectors, and I look at the empirical distribution of the coordinate of, you know, the pair theta 0, theta t. Okay, this converges, you know, for instance, in W2 distance to the law of a pair of random variables, capital theta and capital theta plus 2t z. Okay, where 2t is given recursively by okay, so you know, this in particular will implies that this convergence of empirical distributions in particular implies that if I look at 1 over d.
Andrea,
yeah, I made a mistake here. One second, I need to correct myself because I made a mistake. Let me call this theta tilde it, and really this theorem is about the joint distribution of these two. Okay, of course, you know, if you give me theta tilde it, I know theta t plus 1 I, but for theta tilde it there is a Gaussian limit. So, and here z, okay, here I should write that z is normal 0, 1, independent of theta, and theta is as distribution of p theta. Yes. Michael was asking something.
Oh no, that's what I was going to point out. Yeah.
Oh yeah. Okay, yeah, I made a mistake. So this gives me in particular this kind of theorem. So this recursion is what we call state evolution. And this kind of this type of theorem is nice because it allows me to you know, compute very precisely pretty much in this limit, but pretty much anything I want. For instance, suppose that I say, okay, I want to compute what is the distance between my estimator theta tilde t and theta 0 after t iteration. Well, I can look at this. This is 1 over d sum over I 1 to d of theta tilde ti minus theta 0 I square. Okay, very nice. So this converges to, you know, it's just integrating the function x minus y square versus this measure. So this must converge to the expectation of the function theta plus 2t z minus theta square. Okay, and this is, you know, trivially is just 2t square. All right, so 2t as the, you know, interpretation of the estimate in this sense, or, you know, of course you can look at 1 over d theta t minus theta 0 square. This will converge to, you know, by basically the same argument will converge to the expectation of eta of theta plus 2t z minus theta square. Okay, and so on. So pretty much any quantity that I'm interested in, I can extract from this theorem. So this theorem says that everything is basically characterized in terms of this interesting recursion. So I can, if I can analyze this recursion, and this is a scalar recursion, I can precisely analyze my algorithm. Okay. Now, if you were there the last lecture, oh, I forgot completely about the pause. Sorry. So perhaps I'll pause. in the excitement. So I'll pause 1 minute and ask if there is any question about this.
No problem.
So we have a question. What should the argument inside the eta be in the last line? Okay.
Oh, sorry. There is a second argument here. Here, of course, this is the argument. So I don't know if the question is this one, but okay, I'll answer. This one that I wrote, of course, I missed an argument here. There is theta plus 2tz and alpha t. Okay. So this is simply applying, this general theorem gives me the limit, in other words, for any test function that is Lipschitz continuous and quadratic growth, the psi of theta tilde ti, theta 0i, this tells me this converges to expectation of psi evaluated at theta plus 2t. Z, and this convergence is at t fixed as n and it goes to infinity and theta. So this is what the theorem says. Okay. So this is the argument. So one way to think of this algorithm is that at each time I have an estimate here, theta hat t, and then I compute the residual, so I compute how well that is fitting the data, and then I back project that on the thetas by multiplying by X transpose, and then I take this soft thresholding to get a sparse vector. Okay, so one thing that I want to mention is that if you remember, if you were there last lecture, you remember that we studied the minimizer of the lasso, and we came up with a pair of nonlinear equations that characterize the values of the minimizer, and you'll notice that the pair of nonlinear equation could be written. One of them took the following form. Okay, and the other one, okay, was something like, I brought them slightly different. Okay, so these two equations characterize the minimizer of the lasso, and you will notice that this second equation in particular, this first equation in particular, is just the fixed point of this evolution. Okay, so this is kind of a consequence of the factor is saying that if you choose the alpha to converge at some point and the tau happens to converge, then you are solving, this algorithm is really solving the lasso with lambda related to alpha in this way. So if you find fixed point of the algorithms corresponds to minimizers of the lasso. Okay, so this algorithm is really optimizing the right cost function. Okay, there are other ways of seeing it, but you see also in this way. And the idea is that after any number of iterations, the theorem is saying that after any number of iterations, this theta tilde t is approximately the truth plus something that is normal 0 to square t identity. Okay, so at each iteration, you have a first order method that has the special property that its iterates are approximately Gaussian. Now, a natural question is, can we improve over this specific algorithm that I described? So I have two algorithms I described, one that is a standard proximal gradient, and one that I can, surprisingly, I can analyze exactly because there's a Gaussian limit. All right, so I gave you two algorithms, one that it's very simple, proximal gradient, and one that I can analyze, right? Now, the natural question is, can I improve over this base, this not base, but this soft thresholding AMP?
Andrea?
Yeah.
So there's some question about some notation, which I don't recall. You wrote convergence in LV2. Is that, maybe we should scroll up?
Yeah, perhaps it's my writing.
Yeah, I think it's just a writing issue.
It's
It
just
really is a
writing.
W.
Yeah, it's a W. I started writing. Okay, you can, of course, this implies convergence in W2 is like convergence in weak convergence plus convergence of, second moments. Okay, the reason why, I'm picky about second moments is that, if I only have a weak convergence, then I cannot say anything about this test function, and this test function is something that I'm interested in because it's the natural estimation error, the square estimation error that many people are interested in. Okay, so now I described two algorithms. One was proximal gradient, and the other is this soft thresholding AMP. And okay, the last 5 minutes I want to discuss, can we improve over this soft thresholding AMP? And the answer is yes. Here there is, if you see, there is this soft thresholding function that is used here, and here it appears again in the state evolution. You can choose this, change this eta in any other function that you wish. Okay, and so if you change it to another function, you can consider a general algorithm that does this kind of thing. And then now I will excite this again a scalar. Before was just a sparsity, and now it's a scalar. I will not write explicitly what it is for the moment. I mean, I can write it, but it's not really important. But the interesting fact is that for any such algorithm, the same state evolution recursion holds sigma square just this is replaced by HT. The specific function is. And then you can ask yourself, okay, what is the optimal function that I can put here? And you see that the problem here that appears in this state evolution is really that you are trying to estimate a random variable theta given theta plus Gaussian noise. Right? So how do you minimize this square error? Well, you minimize simply by taking the conditional expectation. So HT of y should be E of theta given theta plus 2t z equal y. Okay, so this is standard. If you want, is just Jensen inequality, right? This will minimize the right-hand side overall possible function of the function choice of the function h. Okay, so if you choose that specific h, now we'll get this iteration. what I call the minimum mean square error of the random variable theta at level 2t. So this is the minimum error that you can achieve with which you can estimate theta when you observe theta plus 2t z. Okay, there is such a thing, and this is just if you want. Okay, so this is the minimum mean square error. Okay, so now, so this gives me an algorithm that improves over, in a simple way, over the algorithm that I just described that was inspired by proximal gradient. Now, what is the behavior, the typical behavior of this recursion here? Okay, the typical behavior of this recursion, okay, it's nice to make a plot of it. Okay, so you have the function here, so tau square, and here the line y equal x. And then there is the function 1 over delta, this function here. Typically it looks something like this, or might look like something like this. And when you run this iteration here, so this is the function sigma square plus 1 over delta MMC 2 square. And when you run this iteration, what happens is that you start at one point, and then you converge to the highest fixed point of this equation. Okay, and there is sometimes multiple fixed points. Now, it's interesting to try to understand how, in the last 2 minutes, how the structure of this fixed point changing as a function of delta. And again, I plot a sketch, and this is a sketch that you will obtain if you look, for instance, at a vector theta that is of the form, for instance, 1 minus epsilon delta at 0 plus epsilon delta at 1. Okay, so some mixture with some zeros and some ones. So very simple Bernoulli distribution. And so delta is really the sample size rescaled by the dimension. And here what I plot is, what any algorithm, various algorithm achieve versus theta 0. And typically what happens is the following. If you look at something like the lasso or other convex methods, you obtain a curve like this that is a continuous curve. And so this is what we'll obtain by the lasso or a convex method, and also by this soft thresholding AMP that I described, the one that uses the eta function. Okay. Now, interestingly, what happens is that, of course, if you look instead of the optimal, so what I described here, with this choice of the function is what I first called the base AMP. Base because at each step you are doing the base optimal operation. Okay, so the mean square error of this algorithm typically behaves like this. Okay, here I plotted that in matches. Okay. Sometimes it has a jump, and then it goes down. Okay, so it's strictly smaller than the optimal algorithm, and it has a jump. Then you can ask yourself, okay, what happens if I don't care about algorithm and I just look at the minimum estimation error that can be achieved by any method, even if it is not computationally feasible. And typically this matches the Bayes AMP until some point, and then jumps earlier and then matches the Bayes AMP after. Okay, so this red line is that the optimal method that is not necessarily computationally feasible. So this amounts to compute the expectation of the whole vector theta given the matrix X and the observation Y. So this will be my theta hat in this case. And instead the purple one is the optimal AMP algorithm, or the Bayes AMP algorithm. Okay, so there is this interesting pattern in which we have three regions. There is a region at small sample size or high noise. So there is two values, delta opt, delta star, and delta alg. There is a region in which delta is between 0 and delta star. Even the optimal method does very poorly. There is an intermediate region in which if you use the optimal method, you do well. You do well, but if you use any first order method, you do poorly. And then there is an easy region. So this is sometimes called the hard region. And then there is an easy region or easy phase in which there is a simple algorithm that achieves the Bayes optimal estimator. This is kind of surprising because in general, computing this posterior is NP hard. And here there is a whole region in which this can be done efficiently. Well, now, there is a broad conjecture here is that this phase diagram is somehow fundamental. That is, no polynomial time algorithm can do well in this intermediate region. Okay, I'll stop here for today, and then the next lecture I will try to complete the general idea of this optimality of Bayes NP, and then I'll move to spin glasses.
So we have a question, which is, why is there a jump?
Why is there a jump? Why is there a jump? Good question. Well, if you give me a specific, so this curve, of course, here depends on this MMSE function. And if you give me the MMSE function, I can, if you give me the distribution of theta, I can compute the MMSE function. And the MMSE function typically is not concave. This is the question. This MMSE function is not concave. And this means that, at very low noise, adding a little bit of noise doesn't hurt you much. So forget sigma. If you forget sigma, this is what really matters is that the MMSE for theta depends on theta. And this, what I'm saying is that this is non-convex, right? It's not concave. So at very small noise, even if you add a little bit noise, that doesn't worsen your estimation error. Or in other words, the estimation error is superlinear in tau square. This is typically what happens, or actually it's always what happens if the probability distribution p theta is discrete, okay? Think, for instance, that theta is, a support on 3 atoms, +1, 0, and -1, right? Now you understand that if I give 0 noise, if I put 0 noise, the estimation error is 0. But if I put a very small noise, you can always reconstruct which of the 3 you come from. You observe, so you have theta and you observe theta plus tau z, where z is Gaussian noise, right? You understand that the error in estimating actually goes down as E minus constant over tau square, right? Because because the probability, you know, if you have a +1, if the real value was a +1, you know, and then you observe it with noise, you get mistaken only if the noise is bigger than 1/2, you know, in a very simple algorithm, right? So this means that actually it will go down as e⁻⁴ So this tells you that this curve goes flat at the beginning. And if it goes flat at the beginning, yeah, okay. So there are chances that there's multiple intersection. And now the delta changes the slope basically of this. You know, it must saturate at some point, this curve, because for instance, in this case, the minimum mean square error is always bounded by 1. So it must saturate at 1, even if there is infinite, or at 2, even if there is infinite noise, some constant. And so the 1/delta really changes the slope of this line. So here we are looking at fixed point of this thing, right? So the 1/delta really change the slope of this line. And so depending on the delta, you intersect this curve at 1 point or at 3 points, right? And at a high noise, you know, what matters is the highest, you know, where the algorithm gets stuck is the highest, noisiest fixed point. And so depending on the values of delta, you'll intersect at the highest fixed point or only at one fixed point. So this region is the region where there is only one intersection here, and this is where there is 3 intersections.
If we have time, maybe it's worth bringing up another question that was coming up about the type of asymptotics we're taking. So the first question was about how in optimization, we typically look at fixed n and d and t going to infinity. And then a follow-up was asking whether the statistical performance for fixed n eventually gets worse as t gets large. So maybe just comment on the sort of fixed t asymptotic.
Okay. So, yeah, so the asymptotic, so fixing t is really means that we are looking at algorithms that have complexity of the order of the matrix vector multiplication, right? So each operation is a multiplication by x or x transpose. This is, so the complexity is of order nd. So this is linear complexity. Now, the question is, can we hope to get much advantage to go beyond linear complexity? In this type of problems, for instance, this linear regression problem, there is type of problems, or in general, this highly symmetric problem with random matrices. There seems to be only one case in which, one type of scenario in which you get a definite advantage. And that type of scenario is typically when the initialization is at an unstable fixed point, right? So one example is the phase retrieval loss function that I was describing before. In this case, you know, if you look at this first loss function from the point of view of landscape, theta equals 0, the natural initialization is theta equals 0. And this is a saddle point of L. And in terms of AMP algorithm, is also a fixed point of state evolution, although an unstable fixed point. Okay, so in that case, in this case, and in similar case, one can do a little bit more work. And one way to do this is you do an ad hoc step to escape the fixed point, the unstable fixed point. So you use a spectral initialization plus order 1 iterations. Another way to escape this fixed point would be to do, so this has been analyzed, at least in some cases. Another way to escape it will be to do order log n iteration with the random initialization. This has not been analyzed as far as I know, but yeah, it would be interesting to analyze. But you know, it ends up going from n to 1 to log n iteration, and that is enough. Now, I don't know of any single example or any interesting example in which, you know, it pays off to do n to the 0.1 iterations of this type of algorithms. I don't know, let me put it this way, I don't know of any examples of this type with random matrices, etc. Now, in optimization, one interested in obtaining fixed n and d and t to infinity, because you're interested in understanding once you're close to the minimum, how fast you approach the minimum. Here we are looking at a different, that is an interesting question of optimization when people tell you, okay, I can solve my problem with precision 10 to the minus 10 or 10 to the minus 15 by only running a few more iterations. For statistical application, it's not that interesting to solve with high precision an optimization problem, because anyway, the data is noisy in itself. So there is some statistical error, and therefore high precision computations are often not that important. But yeah, I mean, it can be interesting to look at for other applications.
I think at this time we're going to stop the recording of the lecture and thank Andrea. And then if there are any further questions, people can ask after.